In this video, we will talk about the interval of validity of an initial value problem. So the interval of validity is the largest interval that contains the input value of our initial condition on which the solution for our problem is valid. So let's say we had an initial value problem and the solution of the problem was y of t is equal to t squared over t minus 2. And let's say that the initial condition of our problem was y of 4 is equal to 8. So as you can see, our solution is not valid when t is equal to 2, because then that would give us a 0 for the denominator. So that means the solution is valid on the intervals from negative infinity to positive 2 and from positive 2 to positive infinity. But the interval of validity has to contain the input value of the initial condition, which in this case would be 4. And so the interval of validity in this case between the two intervals would be this interval from 2 to positive infinity. Now for an initial value problem with a linear first order differential equation of the form the derivative of y plus some continuous function of t that we call p of t times y is equal to some continuous function that we will call q of t, with the initial condition y of some input value that we can call here t naught is equal to some value that we will call y naught. And if the functions p of t and q of t are continuous on some interval between two values, and let's call them alpha and beta, and if this interval contains the input value of the initial condition t naught, then that would mean there's a unique solution to this initial value problem. And if this interval is also the largest possible interval on which both p of t and q of t are continuous, then this interval is actually the interval of validity of our initial value problem. So what this means is, for these types of initial value problems, we don't have to solve the equation to find the interval of validity. Now let's make things concrete by finding the interval of validity of this initial value problem without actually solving the equation. So first, let's put it in the correct initial form by dividing the equation by t squared minus 9. That will give us the derivative of y. And I'm just using the Leibniz notation here. With respect to t, plus 2 over t squared minus 9 times y is equal to the natural log of the absolute value of 20 minus 4t over t squared minus 9. Now, as you can see, this function is not continuous when t is equal to positive 3 and when t is equal to negative 3, because at those values of t, the denominator becomes 0. Same thing can be said about this function, but this function is also not continuous when t is equal to 5, because that would give us the natural log of 0, which is invalid. So the interval on which both of these functions are continuous are the interval negative infinity to negative 3, and from negative 3 to positive 3, and from positive 3 to positive 5, and from positive 5 to positive infinity. So out of all of these intervals, the interval of validity of our problem is the one that contains the input value of our initial condition, which in this case is 4. So the interval of validity is this one, the one that is from but not including 3 to but not including 5. So now let's consider an initial value problem with a nonlinear differential equation in the form the derivative of y with respect to t is equal to some function of t and y, and let's call it f of t and y. And the initial condition would be y of some independent variable, let's call it t naught, is equal to y naught. And if this function f and its partial derivative with respect to y are both continuous in some rectangle, let's call it alpha to beta, and gamma to delta. And if the point t naught, y naught is contained in this rectangle, and t naught and y naught are the input and output of the initial condition of the problem, then our initial value problem has a unique solution on an interval that's contained in the rectangle and that contains the input value of our initial condition. So basically, if you have a ty plane, so this would be the t-axis and this would be the y-axis, and if the function f and its partial derivative with respect to y are both continuous in some rectangle, and so this right here would be alpha, this would be beta, and this would be gamma, and this would be delta. And if the point t naught y naught is contained within this rectangle, which means this right here would be t naught, and this right here would be y naught, then there is a unique solution to our problem on some interval that contains t naught but is contained between alpha and beta. So unlike problems with linear differential equation whose interval of validity was only affected by the input of the initial condition, with the nonlinear differential equation it may also be affected by the output of the initial condition. Now let's take a look at this initial value problem with a nonlinear differential equation, and its initial condition has the arbitrary y naught as its output value. And this will help us show that the interval of validity of problems with nonlinear equation can depend on not only the input value but also the output value of the initial condition. And unlike with linear equations, we cannot find the interval of validity of nonlinear equations without solving the equation first. But before we solve this equation, we can actually check to see if our problem has a unique solution. Now remember that if this function y squared and its derivative with respect to y are both continuous on some open intervals that contain the values of the initial condition, then there's a unique solution to our problem contained within those intervals. And as you can see, both the functions y squared and the derivative with respect to y, which is 2y, are both continuous functions. So there is a unique solution to this problem. And to solve this equation, which is a separable differential equation, we will start by dividing both sides by y squared, and we will get y to the negative 2 times the derivative of y with respect to t, and we'll use the Leibniz notation here, is equal to 1, and then we can separate the derivative and integrate both sides, and we would get the integral of y to the negative 2 dy is equal to the integral of dt. And that will give us negative 1 over y is equal to t plus the constant of integration. At this point, we can solve for the constant by plugging in the initial condition values, and that will give us negative 1 over y naught is equal to 0 plus c, or just c. And so we can plug that back into the solution, and we get negative 1 over y is equal to t minus 1 over y naught. So now we can solve for y of t by dividing by negative 1 and taking the reciprocal from both sides, and that will give us y of t is equal to 1 over y naught minus t. And we can simplify this by multiplying it by y naught over y naught, which will give us y over t is equal to y naught over 1 minus y naught times t. So this is the solution to our problem, and the only thing that would make this function invalid is if the denominator is 0. So to figure out what the interval of validity is, we can set this term 1 minus y naught times t to 0 and then solve for t. And when we do that, we get t is equal to 1 over y naught. And so the interval on which our solution is valid is from negative infinity to 1 over y naught, and from 1 over y naught to positive infinity. And out of these intervals, the interval of validity would be the one that contains the input value of our initial condition, which was actually 0. And as you can see, that would depend on what the value of y naught is, because if y naught is a negative number, then that means 1 over y naught is also a negative number. So in that case, the interval that would contain 0 would be the second interval, so that would be our interval of validity. Now if the y naught value was greater than 0, or if it's positive, then 1 over y naught is also positive, which would make the first interval, this one, it would make that the interval of validity, because that's the interval that contains 0, which is our input value of the initial condition. So as you can see, for problems with nonlinear differential equations, the output value of the initial condition could affect the interval of validity.